Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good day and salam sejahtera to everybody. Today our chapter continue with combustions in chapter number 7, part 3. First of all, I would like to make an acknowledgement. Thank you very much to Dr. Azmi Hussein, one of my clique, because of his efforts to complete this slide of thermodynamics 2 or heat transfer. Okay, today I will start this topic by showing first the objective that you should be able to know in this chapter. So the objective of this chapter is only one. That's mean the last one. Should a student should be able to apply the first law of thermodynamics to combustion processes and enthalpy of combustions. That is only one objective you should know within this chapter. Okay, let's look on this to the topic. I go to the page of this topic. Okay, enthalpy of formations and enthalpy of combustions. Before I explain more on the enthalpy formations and combustions, let's look again what is the definitions of enthalpy. Okay, you have studies in thermodynamics 1 or the previous course, the definitions of enthalpy. Okay, the enthalpy actually is a measurement of energy in a thermodynamic system. The quantity of enthalpy equals, or the definitions of enthalpy is the quantity that equals to the total content of heats of the system equivalent to the system internal energy plus the product of volume and pressure. And you know that the volume and pressure is work energy. So this by in terms of mathematical formula, the enthalpy H is equals to U plus PV. So that is the enthalpy. The microscopic form of energy of a substance consists of various form of energy, such as sensible and latent energy that is associated with a change of state, chemical energy associated with the molecule structure, and nuclear energies. That means associated with a atomic structure. So in this topic, we don't really attend to deal with nuclear energy. So as you know, previously we have studied that we study an energy that it know, okay, chemical energy, since the system involved, we consider no changes in their chemical structure to no changes in chemical energy. So now, at these stages, we will consider the chemical reactions, because in the combustions there will be the chemical reactions. Okay, during the chemical reactions, some chemical bonds that bind the atoms into molecules are broken and new ones are formed. The chemical energy associated with this bond in general is a difference for the reactant and the products. Therefore, a process that involves chemical reactions involve changes in chemical energy, which must be counted in an energy balance. So by assuming the atom of each reactant remain intact, that means no nucleus reactions, and disregarding any changes in kinetic and potential energies, the energy change in the system during the chemical reactions is due to the change in state and change in chemical compositions. That means, as you see in these equations, the total energy of the system is equals only the total of energy state plus the total of energy chemicals. In thermodynamics, we are concerned with the changes in energy of the system during a process, and not the energy values at the particle state. Okay, that you all have to remember. Therefore, we can choose any state as a reference state and assign a value of 0 to the initial energy or enthalpy of substance at that state. When a process involves no changes in chemical compositions, the reference state chosen has no effect on this result. When the process involves chemical reactions, however, the compositions of the system at the end of the process is not longer the same as that at the beginning of the process. In this case, it becomes necessary to have a common reference state for all substances. So the chosen as a reference state is actually 25 degrees Celsius and 1 atm, uh, which is known as standard reference state. So this property value at the standard reference state is indicated by subscript degrees. Okay, okay. As you see in this slide, uh, the symbol H here has a degrees at a subscript of this H. Okay, now let's consider the formation of carbon dioxide. Okay, let's see on this slide at the right side. Okay, okay, a moment. Okay, these two elements, that mean from carbons and oxygens, during a steady flow combustion process, As you see, both carbon and oxygens enter the combustion chamber at 25 degrees Celsius and 1 atm. Okay, the carbon dioxide form during the process also leave the combustion chamber at 25 degrees and 1 atm. So it have same state. Okay, and as you see here, the combustion of the carbons is an exothermic reactions. That means the reaction during this uh, exothermic is the chemical energy is released, okay, in the form of heat. That means as you see in these pictures, okay, it's called exothermic. If it is called as endothermic, the heat is absorbed by the system, okay, in the combustion chamber. Therefore, some of heat transfer from the combustion chamber to the surrounding during the process, which is 393,520 kilojoule. That means it's formed as a CO2 or carbon dioxide. So the process that's been described above, we can assume that or it's not involved with no work interactions. Therefore, for the steady flow energy balance reactions, the heat transfer during this process must be equals to the difference between the enthalpy of the products and the enthalpy of the reactants. Okay, so that is heat transfer Q is equals to H product minus H reactant is equals to negative 393.5 to 0 kilojoule per kilomole. So the unit is kilojoule per kilomole because it is mentioned in the chemical reaction. So both of reactant and the product are at the same state. The enthalpy change during this process is solely due to the changes in the chemical combustions of the system. This enthalpy change is different from different reactions, and it is very disabled to have a properties to represent the changes in the chemicals energy during reactions. So these properties actually is a enthalpy of reactions. That means HR, which is defined as the difference between the enthalpy of the products at the specific state and the enthalpy of the reactants at the same state for the complete reactions. Okay, that is the definitions of the enthalpy of reactions for combustion processes. Okay, for combustion processes, the enthalpy of reactions is usually referred to the enthalpy of combustions. That means HC, which it represents the amount of heat released during the steady flow combustion when 1 kilomoles of fuel is burnt completely at a specific temperature and pressure. And this can be expressed in the mathematic model as HR, that's mean enthalpy of reactions is equals to HC, enthalpy of combustions, and these two properties is actually is equals as H product minus H reaction. The enthalpy of combustions is obviously a very useful properties for analyze the combustion processes of the fuels. However, these are so many different fuels and fuel mixtures that is not practical to list HC values for all possible cases. Besides this, entropy of combustion is not much used when the combustion is incomplete. Okay, so this is quite difficult to measure. So therefore, a more practical approach would be to have a more fundamental properties to represent this chemical energy of an element or compounds at the same reference state. So what should you know? The new properties named as the enthalpy of formations. Okay, enthalpy of formation. That means HF subscript of degrees. Okay, this is the term that will be known as the enthalpy of formations, which we can view as the uh, enthalpy of a substance at a specific state due to its chemical compositions. So the simple definition for this enthalpy of formations is the amount of energy absorbed or released. That means endothermic or exothermic as a component is formed from its stable elements during the steady flow process at the specific state. So for these properties, we can use, or also if we want to do the calculation or analysis, we can use the table A26, okay, for enthalpy of formations. Okay, to establish the starting point, okay, we assume that the enthalpy of formations of all stable elements, okay, stable elements such as O2, N2, H2, and C are value of 0 at the standard reference state of 25 degrees Celsius and 1 atm. That is HF is equals to 0 for all stable elements. Okay. So in here, what I want you to know is for the stable element. What I mean by the stable element? We take example as a stable element of nitrogen. Okay, at the standard reference state is diatom nitrogen. That means N2, not monoatom nitrogen. That means only one atom. Okay. If the element exists is more than one um, stable form at 25 degrees Celsius and 1 atm, one of the form should be specified as the stable form. Okay, for example, carbons, the stable form is assumed to be graphite. Okay, not diamonds. Okay, that is for carbons, different between hydrogens, nitrogens, and oxygens. Okay, so let's look at the right side. This one, this is all at the same same state, 25 degrees Celsius at it reactants, and also product 25 degrees Celsius 1 atm. So as we consider the formations of CO2, that means CO2, the formations product is the compound. from its elements carbon and also CO2 oxygens during the process was determined to be a negative 393,520 kilojoule per kilomole carbon dioxide. However, as you see at these pictures, uh, enthalpy react is equals to zero, since both reactant are element at a standard reference state, and the product consists of 1 kilomole of CO2 at the same state. Therefore, the enthalpy of formations of CO2 at the standard reference state is a negative 393,520 kilojoule per kilomole. Okay, so to make it more understand, after this I will show some of the examples. Okay, one of the examples how we can analyze and calculate this case. Okay, as you see here, the negative sign due to fat formations for the compound indicated that the heat is released during the formations of that compound from its stable element. Okay, if the signage is positive, the value indicates heat is absorbed. Okay, as I mentioned earlier, we can see table 26 for entropy of formations. Okay, I will show you table uh, 26. Okay, wait, 9, 3, 4. Table 26. Okay, this is table 26. Okay, the entropy of formations. As you see here, the substances, carbon, hydrogen, and etc. And this is entropy of formation. Okay, entropy of formations. If you go up slide, you will see various properties for elements. That means table 24 for oxygens, and it have H enthalpy bar. This is enthalpy at standard reference state. Okay, this is the temperature. Is the standard temperature standard reference state is 25 degrees Celsius. That means Kelvin, the temperature is 298. Okay, 298. So the entropy of combustions here is 6,852. This is for water vapor. Table 23, still for water vapor. This is for hydrogens. Table 22. This is for carbon monoxide. Still for carbon monoxide, carbon dioxide, and so on. Okay, so you can just look on your properties tables, find table 20 to 26. Okay, it will show to you the enthalpy of combustions and also enthalpy of uh, formations. Okay, we look the examples. Okay, determine the enthalpy of combustions of methane, that's mean CH4, at 25 degrees Celsius and 1 atm. using the enthalpy of formations data from table A26, assuming that the water in the products is in the liquid form. Okay, to solve this problem, first we have to make some assumptions. Uh, the assumption that you have to make is the enthalpy of the combustion of fuels is to be determined using enthalpy of formatting data. Okay, and then the water in the products is in the liquid phase. So from there, the properties that you have to find is the enthalpy of formations at 25 degrees Celsius and 1 atm. So let's look on the if you look on the what we call the tables A26, look at the table A26, okay, for entropy of formations. So before you want to look the tables, you have to analyze the equations, chemical equations. So the stoichiometric equations for these reactions will become CH4 plus air, okay, 2 oxygen plus 3.676 nitrogens. It will become the product CO2 plus 2H2O water plus nitrogen. So as you see in these equation reactions, both the reactant and the product are at the state at the standard reference state 25 degrees Celsius and 1 atm. So also noted that nitrogen and oxygen are stable elements, and their through their enthalpy is of formations is 0. Then the enthalpy of combustions of methane will become the formula Hc is equals to H product minus H reactant. So in here H product has 2. Okay, this one and 2. So carbon monoxide, carbon dioxide, and also hydrogens, that is products. But for reactant is only methane. So the total of number of mole, okay, times the enthalpy of formations products minus the total of mole times enthalpy of combustions formations reactant. So as I mentioned, for product it has two elements or compounds, okay, not element, compounds. So carbon dioxide plus water H2O minus um, methane. Okay, so from table 26, we find these three compounds. That's mean water. It assumes that the product is in the liquid state. So the water is formation, entropy of formations if water negative 285830. Then for uh, another compound is carbon dioxide. Okay, negative 393520. And other ones is methane. Okay, negative 74850. That is enthalpy of formations for these three compounds. So then we put on the equations. Okay, put on the equations. For Hc is equals to 1 kilomoles. That's mean for carbon dioxide only 1, water 2. So 1 time this H formations plus 2 kilomoles time the value of Hc, Hf for water, and minus 1 for methane kilomole times negative 74. Okay, please make the corrections in your slide. This is 74, not 4, 74. Okay, so from there you calculate, it will give the enthalpy of combustions for this uh, products is negative 890,330 kilojoule, okay, per kilomole of CH4, and the value you have is negative. Okay, that's mean this is at this is at zo okay, exothermic. Okay, exothermic meaning that the system is release heat. Okay, not absorb heat. So the system is release heat. Okay, this is how you calculate the enthalpy of combustions, and also how you use enthalpy of formations using tables A26. Okay, we continue with next slide. Okay, this is slide is about the first law analysis of reacting system. Okay, will look only on the steady flow system. So, as you learned previously, okay, the energy balance or the first law of thermodynamics are applicable to both reacting and non-reacting system. However, chemical reacting system involve changing or changes in their chemical energy, and thus it is more convenient to rewrite the energy balance reaction so that the changes in chemicals energy are explicitly expressed. Okay, so how we can do this? First of all, we will look on the steady flow system. Okay, so actually this steady flow system, what I want to talk about, this is in the actual process, a combustion process. So as you look in this slide, you see that the standard reference state is not at the same state. Sorry, the state at reactants and also at product is not as a same state. So we cannot use standard reference state. So this is the actual combustion process where the temperatures of the reactant and products are not at a standard reference state. Okay, so here, this is 7 degrees Celsius, and our output product is 1500 kelvins. Okay, so this is 25 degrees Celsius. That is this is not at a same state. Is we have this case, then the equations balance energy can be rewrite, and also can be expressed the enthalpy of the components as this way. Okay. So the enthalpy of the chemical components at the specified state is the sum of the enthalpy of the component at 25 degrees Celsius 180 m and the sensible enthalpy of the component relative to 25 degrees Celsius and 180 m. So this is how we express in the actual combustions process when we want to find the enthalpy. So the enthalpy is equals to number of moles n times the enthalpy of formations at the standard reference state, where we can look in the or we can refer to the table A26, various substances, plus the sensible enthalpy relative to standard reference state. That means H bar minus H bar degrees. Okay, this can be you can refer to the table A18 to 24 at the various substances. Okay. Where the term in the parentheses represent, okay, that means they represent the substitutable entropy relative to the standard reference state, and which is the difference between H bar, the H bar, as I mentioned, this is the sensible energy at the specified state, and H bar degrees, this one, this is the sensible entropy uh, at the standard reference state of 25 degrees and 180 m. So the definition enable us to use entropy values from table regardless of the reference state used in their constructions. Then the energy balance relations is written without the work, okay, term, since most steady flow combustion processes do not involve any work interactions. Okay, this is the normal terms that you have also known. Okay, combustion chamber normally involve heat output but not heat input. Then the energy balance for the typical steady flow combustion processes will become as mentioned. Okay, this is the first heat out is equal to the energy in by mass per mole of fuels minus energy out by mass per mole of fuel. N represent the number of moles of the reactant R and the product P. Okay, R is reactant, P is product. Note that NR is equals to 1 for the fuels, and the other NR and NP values can be picked directly from the balance combustion equations. Okay, taking heat transfer to the system and work done by the system to be positive quantities. So the energy balance reaction just discussed, the mean we can express as like the I showed in this red, okay, formula. So this is how you want to find entropy product, and this is how you can find entropy react. Okay, we can to know more about this first law analysis for steady flow system. Let's look on the examples. Okay, let's look on the examples. Okay, the ethane gas C2H6 at 25 degrees Celsius is burned in the steady flow combustion chamber at the rate of 5 kg per hour with the stoichiometric amount of air, with it preheated to 500 Kelvin before entering the combustion chamber. The analysis of the combustion gases reveals that all the hydrogen in the fuel burns to H2O, that's water, but only 25% of the carbons burns to CO2, and remaining 5% forming CO. If the product leave the combustion chamber at 800 Kelvin, determine the rate of heat transfer from the combustion chamber. So this is the pictures how this statement meaning. Okay. So as you see here, inlet or adtant, reactant, and also product at not on the same state. So this is the actual process that happened. To analyze this and so to solve this, uh, we have to make some, of course, some examples. Sorry, not example, of course, assumptions. Okay, we have made some assumptions. Okay, the assumption firstly, this is steady operating condition exists. Okay, air and combustion gases are ideal gases. Kinetic and potential energies are negligible, and combustion is complete. Okay, so that is assumptions that we have to make. So analyze these theoretical combustion equations of C2H6 is like this. Okay, this is a reactant plus air. The product, complete product, will become CO2, water, and also nitrogens. Okay. So firstly, you have to find ATH. This is stoichiometric coefficients and it is determined from the O2 balance. Okay, energy equation balance for this left and right side. And so from here, ATH stoichiometric coefficient will you will get 3.5 value, and then the actual conversion equation can be written as put 3.5 in the in front of the air, then all of the energy balance you have to make it actual combustions. Okay, like this. Okay, I don't want to explain more about this how we rewrite this equation, because I have discussed and show you how to get this actual combustion equations. Okay, how to solve this by using left hand or right hand balance equations. Okay, then by applying the heat transfer for the combustion processes using energy balance applied on the combustion chamber with work is zero. Okay, we ignore work interactions here. It will reduce to negative Q out is equals to total of moles times the enthalpy of combustions. Okay, the new formula when we use for the actual combustion process, minus, okay, this is for product minus reactant, same equation that I mentioned. So from here also, assuming the air and the combustion products to be ideal gases, we have H is equals in terms of temperatures difference. From the tables, A26, you will find all the substances involved, and then find the enthalpy uh, formations for these substances. Also, the enthalpy at 500 K that involved at standard reference state. That means at 25 degrees Celsius, or enthalpy at 298 kelvins, and also enthalpy at 800 Kelvin. Okay, this is all the enthalpies for combustions and for formations. Using these all values that have you determined, referred to the table A26, then put in or use these all values into the equations that have you defined. Also regarding to the mole number of mole that have in the chemical equations, then calculate the sum of these equations, then you will get the Q is 1201005 kilojoule per kilomole C2H6. This actually a negative. So for the negative, that means the system will release heat. Okay, that means the reaction release heat. It is the exothermic reaction. Okay, right, the thermic reaction. So from there, the rate of heat transfer uh, for given mass flow rate, you can calculate using this formula where Q dot out is equals to N dot Q out. You have know, or you have determined Q out. So now from here, you know that from N dot, the formula is M dot per M, where we can get this is, you know, the M dot actually is equals to uh, N M. Okay, number of mole times the weight, the mass of mole. You will get M dot. So from here, in the question, it has mentions the mass flow rate. Okay, given to you mass flow rate. So put the value into these equations. Then you will get mass flow rate of 3 kilogram per hours. 3 kilogram. So here is it 3? Rate of 5 kilogram. Okay, sorry, 5 kilogram, not 3. Okay, so then the rate of mass of 5 kilogram, this is not 3, this is 5. Okay, 5 kilogram. And then calculate, then you will get the answer is 20170 kilojoule per hour. Okay, kilojoule per hour. This is how you can find. This is how you can find the power or Q dot, because in this question example, determine the rate of heat transfer from the combustion chamber. So the rate of heat transfer, after you have calculate, it will give this value. Okay, that's it for today. So this is last chapter for this course, and also part 3 for combustion. So I hope you you can get all the knowledge, or also the informations of the thermodynamics too, or also the heat transfer. So I think that's all. As I said, or as I mentioned earlier, if you want to know more, please read a book, okay, or a reference book, not just refer to the simple notes and also the lectures of other teachers or lecturers. Okay, you have to read a book to know more. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh, dan salam sejahtera. Kita jumpa lagi, insya Allah.